Okay, so this unit 6, is going to focus on some kind of famous, I call them canonical discrete random variables there because they're like part of the probability canon. Anybody who takes a probability course needs to learn about these famous random variables. And so just to sort of locate what we're doing right now. So far, when we've talked about random variables, we've kind of made them up as we went along for the scenarios we were interested in. So we're kind of defining them in an ad hoc way to go with some kind of story. And that's fine. We can always do that. And everything we've learned is so far has equipped us to do that. But there's some types of stories that arise so often that the random variables we use start to seem familiar, and that's kind of why they're in the canon. So what I want to do is go through the most common ones. And something that I've done for Unit 6 is I've made this table of the random variables that we're going to go through in the various lessons here. And that's on the website as its own document, and I'm going to be kind of going through it in chunks in the individual lessons. So for each of these random variables, they have names, so I'm telling you the name, and a little brief description of the story that goes with them. The parameters. Okay, so when I say that's a random variable that corresponds to a situation, it's usually like a family of situations that you need some parameters to pin down the specifics. So these columns are kind of the setup, and then the other columns are just some reference materials. What's the probability mass function for this random variable? What does its mean, and what is its variance? Okay, so this is kind of like a reference here. This nothing special about this table. There's versions of it in lots of books and online and things like that, but it's just sort of nice to have all the information summarized. We're going to derive, we're going to not really formally derive, we're going to talk through the logic of the PMFs of some of the random variables. Some of them we're just going to say that's what it is, and if you're interested, you can find the formal derivations in books or online. Okay, so let's kind of zero in here on the first two lines. So the first line in the table is the Bernoulli random variable, and we've been talking about things like Bernoulli random variables quite a bit. Bernoulli random variables take two values, usually think of it as 0 or 1, and we use them to model the success or failure of a single event. So a coin flip is a Bernoulli trial. Any kind of either or decision is a Bernoulli trial. What's important about the Bernoulli trials is that the probability of a success, of a heads, of getting a 1, whatever, doesn't have to be 50-50. Okay, so if we think of a Bernoulli trial as a coin flip, the coin doesn't have to be a fair coin. Okay, when it is a fair coin, we have p equals 0.5, but we can think about other cases as well. So the Bernoulli random variable, as I say, we've been working with them all along, just not calling them that. I'm including it here because some of the other random variables that we're going to talk about are based on Bernoulli trials. So the Bernoulli trial is just like one flip of one coin, and nothing really much to say about the probability mass function. The probability that it's a 1 is p, so the probability that it's 0 is 1 minus p, and we're used to writing the PMF of a Bernoulli random variable in our kind of table form. So let's just sort of remind ourselves of what that looks like, that x takes value 1 with probability p and 0 with probability 1 minus p. That's another way of writing this PMF. So as we go through the lines of the table to the somewhat more complicated PMFs, what you want to do is thinking about relating these functions to the tables that we've been constructing so far, because they're giving the same information. All right. So as I said, the Bernoulli trial, this like one thing that can have either one outcome or another, can be the basis of more complicated questions. And for the rest of this lesson, we're going to talk about specific, more complicated questions. And that question is, if we flip the coin n times, what is the probability that we get a specific number of heads? If we do n Bernoulli trials, what is the probability that I of them are successes? That is the answer to that question is given by the binomial random variable. Okay, so the binomial random variable has the same parameter as the Bernoulli trial that it's based on, but we also have another parameter that tells us how many trials there are. So how many times are we flipping that coin? With these random variables that are based on Bernoulli trials, we are assuming that the trials are independent. Okay, we'll get to one random variable that doesn't assume independence, but for right now we are. Okay, so again, the coin flip is a really good metaphor for events that are either truly independent or close enough to independent that you don't want to deal with a dependency and you're willing to make that assumption. Okay, so let's kind of go through an example of a binomial random variable with n equals 3 and p equals 0.25. Okay, so if we're thinking about a coin, it's not a fair coin. It's biased towards tails, right? The probability of heads is only 0.25. And we're going to flip that thing 3 times, or switching out of the language of coin flips and into the more sort of general probability language, we're going to do 3 independent trials, each of which has a 0.25 probability of succeeding. And we want to know the distribution of the number of successes in those n trials. That's what we're going to derive here on the board. It's going to help us for this. I picked picked a nice small number of n here so that we can write down the whole sample space of outcomes. That's going to help us wrap our brain around what we're doing here. So if n equals 3, the sample space here, how can those 3 trials come out? Well, one way they can come out is we can have 3 successes. We can have a success followed by 2 failures. We can have a success, failure, another success. We can have failure, success, success. We can have success, success, failure. We can have failure, failure, success. We can have failure, success, failure, or we can have 3 failures. I did something not super awesome here by accident, but since it's something that you might be prone to doing too, I'll just point it out and move on. Normally, when I'm writing out something like this, the first thing I'm thinking in my mind, I'm thinking, okay, so how many things am I going to be listing here? Okay, it's 3 outcomes, each of which can take 2 values. So it's 2 to the 3rd power. Okay, 2 outcomes for the first times 2 outcomes for the second times 2 outcomes for the third. So I'm thinking I should be having 8 elements here. And if you heard my voice getting slow at the end, it's because I was counting to make sure I got to 8 there. What I would usually do when I'm listing these is I'd usually be a little more systematic than I was here. I guess I was maybe using a different system than my normal one. Usually what I would do is list all of the ones with 1 success first, then all of the ones with 2 successes up to 3. So I did it in kind of a weird order. It's good as you're developing your own system for working through these problems to come up with your own idea of what's a good way to enumerate when you're going to do enumeration. Okay, so I didn't enumerate systematically here, but with n equals 3, we can just look at things and make sure it's okay. All right, so what I want to do now is, in looking at this sample space, I want to derive this, okay? I want to convince ourselves that the probability that x takes the value I for each I is equal to this expression, n choose I times p to the ith power times 1 minus p to the n minus ith power. Sounds kind of gnarly, but you'll see it kind of emerges pretty naturally. So what we want here for our random variable, I'll kind of put the BI down there to remind us that it's a binomial with n equals 3 and p equals 0.25. So n trials, success probability 0.25. And I want to do the table of probabilities the same way we've always been doing. Okay, I want to write down the binomial probabilities for this random variable. So with 3 trials, the possible number of successes, right? Because that's the story that goes with the binomial random variable. That's what x represents, is the number of successes. Let's first just think about the values it can take. Well, I can run that trial 3 times and I can get 0 successes. I can do it and get 1. I can do it and get 2. I could do it and get 3. Okay, so the possible values that this binomial random variable can take are 0, 1, 2, and 3. And you kind of see in the table, I've listed the possible values that I can take. It's possible to get 0 successes, and if there's only n trials, you can't get any more than n successes. Okay, so let's now think about the probabilities for each of these. The probability that x equals 0 is, what is that? Well, that's the probability of FFF. Okay, that's the only one of these outcomes that has 0 successes in it. And remember, these are independent trials. So the probability of getting 3 fails in a row, because the trials are independent, we can just multiply the probability of a fail times the probability of a fail times the probability of a fail. Okay. So that probability is 0.75. Okay, right? If the probability of a success is 0.25, the probability of a fail is 0.75, and we're raising that probability to the power 3. Okay, okay, so that's so far so good. Gets a little more complicated as we increase the number of successes we're looking at. So as we're thinking about different possible values for this same random variable. Okay, so for I equals 1, the probability of that is the probability, let's see. This is, no, that's not. This is 1. This is where a case where we have 1 success. This is a case where we have 1 success, and this is a case where we have 1 success. So maybe I'll actually go ahead and do that in a color here. So we've got 1 success here. There's 2, there's 2, there's 2. Here's 1 success, and here's 1 success. Okay. So that is the probability of success, fail, fail, plus the probability of fail, fail, success, plus the probability of fail, success, fail. And the thing that we're thinking about here is that each of these outcomes has 1 success. Okay. We're adding the probabilities because these are mutually exclusive events, right? They're mutually exclusive because this is like an outcome. That's a different outcome. So if it's this outcome, it's not that one. And each of these outcomes, again, has a probability that we calculate by multiplying the probability of this success times that fail times that fail. And we're allowed to multiply the probabilities here because we're assuming the trials are independent throughout. That's part of the binomial random variable, is that the trials are independent here. Okay. So actually, I think I'm going to give myself a little more space because I'd like to write the probabilities right under that. Okay, so this probability here is probability of success is 0.25 times probability of failure is 0.75 times another failure, 0.75 squared. Okay, so this probability is that. Plus plus, where'd my pen go? Plus 0.75 times 0.75 times 0.25 squared times 0.25. Okay, so here's the probability of this one outcome, probability of the first outcome, the second outcome, the third outcome that belongs in this event here. That is 0.75. This should not be an equal sign, it should be a plus sign. We're adding the probabilities. 0.75 times 0.25 times 0.75. Okay, look what we got here. We've got really the same number, just with the factors written in different orders each time. So it's 3 times 0.25 times 0.75 squared. Okay. Let's do the probability that there are 2 successes in the end trial. So that's I equals 2. So it's going to look a lot like I equals 1. So what are the ways that we can get that? Let's see, here's one with 2 successes. Here's an outcome with 2 successes, and here's an outcome with 2 successes. So we're going to calculate the probability of each of those individual outcomes and add them up. So that is the probability of success, fail, success, plus the probability of fail, success, success, plus the probability of success, success, fail. Okay, and just as I did before, I'll write the numbers underneath. So the probability of success, fail, success is 0.25 times 0.75 times 0.25. Let's just write it. 0.25 times 0.75 times 0.25. Probability of fail, success, success, that is 0.75 times 0.25 squared, plus the probability of success, success, fail, that is 0.25 squared times 0.75. Same story here. We have, essentially the same number in all 3 places, just with the factors written in different order. So consolidating that, it's 3 times 0.25 squared times 0.75. Okay. All right. And then for the third possibility here, for I equals 3, and this one's a little bit simpler. There's only one way we can have 3 successes. That's by having 3 successes in a row. So that is the probability of 3 successes in a row, and that is 0.25 to the 3rd power. Okay. So what we did here is we just derived the whole PMF for the binomial random variable. Okay, all right. Let's think about what that means. And what I'm going to do is I'm going to take some of this information over to the next page here. And yeah. Okay, so reminding ourselves what we're looking at here is a binomial random variable with n equals 3 and p equals 0.25. And what we'd done before is we derived the probability mass function for this x of 0, and that was 0.75 cubed. The probability that x was 1, that was 3. I'm writing this in kind of an intentional order to help us see how these numbers fit the formula here. So that was 3 times 0.25 times 0.75 squared. Probability of 2 was 3 times 0.25 squared times 0.75, and the probability of 3 is 0.25 cubed. Okay, so the way we got these probabilities was by looking at the outcomes that corresponded to each of these events. The event of 0 successes, the event of 1 success, of 2 successes, and of 3 successes. And what I want to do now is show you that the probabilities that we got from the story, from looking at the sample space and figuring out the probabilities, that those match what we would get from the formula here. Okay, so let's do that with a different color here. So just, I'll write the formula a little bit bigger here. The probability that X takes value I. So I here is the set of values that the random variable can take. It's the argument of the function. So it's like, you're telling me how many successes you want. The function is giving me the probability of that number of successes. And the assertion is that that is n choose I times p to the ith power times 1 minus p to the n minus ith power. And I think for many people, you look at this formula, it just seems like there's a lot going on, but it's really, if we walk through it, there's nothing weird here. It's pretty straightforward. Okay, so let's just plug in here px for I equals 0. And so what we have, we're going to plug in for the values of I, each of these, also for n, which will always be 3, and for p, which will be 0.75, which of course means that 1 minus p is 0.75. Okay, so probability of 0 is 3 is our n, choose 0, times 0.25 to the 0 power times 1 minus p to the 3 minus 0 power. All that was is just plugging in those numbers, not thinking too hard about it. Okay, now we're going to also kind of keep our mind focused on the little picture here. Just think about what these numbers mean. Okay, 3 choose 0 is 1. Okay, anything choose 0 is 1. You can remember that with the story of what we're talking about. How many ways are there to select 0 things from a set of 3? There's only one way to do it. You select 0 things. You can also evaluate any of these binomial coefficients, these combinatorics, with calculators. Some calculators will have buttons for it. You can type 3 choose 0 into Google, and Google has a calculator that will tell you that. You can also expand this into 3 factorial over 3 factorial times 0 factorial and work that out. However it is, this will be 1. Okay, so let's do this calculation. We might also remember that anything to the 0 power is 1, and good, that gives us a 1 here, times 1 minus p to the 3 minus 0 power, that is 0.75 to the 3rd power. So what we're getting over here is 0.75 to the 3rd power. And yes, indeed, what we get by plugging into the formula exactly matches what we got by just sort of figuring it out from the binomial random variables story. Here. Let's keep going. Let's do that for p equals 1. Okay, so again, over on this side, all I'm doing is plugging in numbers into this formula. Okay, so for p of 1, that's going to be 3 choose 1 times 0.25 to the power 1 times 0.75 to the power 2. 3 choose 1 is 3. That gives us 3 times 0.25 times 0.75 squared. And once again, we're getting the same answer. Probability that I equals 2 when we have n equals 3 and p equals 0.25 is 3 choose 2 times 0.25 squared times 0.75 to the 3 minus 2 power. 3 choose 2 is also 3 times 0.25 squared times 0.75. And then the last number that we could plug in to our PMF here is 3. 3 choose 3 times 0.25 to the ith power, that's 3, times 0.75 to the n minus ith power, that's 0. 3 choose 3 is 1. If you have 3 elements, there's only one way to choose 3 things. 0.25 cubed is 0.25 cubed, and 0.75 to the 0 power is 1, just like anything else. So, as promised, the numbers that we get here match. This matches this. This matches that. This matches this. And this matches this. Okay. So when n equals 3, it's not a problem, and in some ways it might even be better to just figure out the probabilities from first principles, not to look at a formula like this. But when n gets big, you really don't want to write down that whole sample space and figure out the probabilities. So what we're doing in this formula is we're memorializing a pattern that holds even when n gets really, really large here. Okay, just again, convincing ourselves that this is correct. Another thing we might want to do is make sure that the probabilities sum to 1. Okay, and so we could, in fact, calculate these out, and we would get, this works out to be 0.429. This works out to be the same number. That won't always be true. It's comes from the fact that we have 3 trials and that the success probability is 1/3 of the failure probability. It's kind of a coincidence here. The probability for 2 works out to be 406, and for 3, 0.0156. You can check these numbers yourself, but they do indeed sum to 1. Okay, so even though either path to getting this probability mass function seems kind of circuitous, we're still getting a set of probabilities for all the possible realizations of the random variable that's the answer to this question, and those probabilities always sum to 1. Okay, so that kind of core of basic probability is still applying here. All right. One last comment on the binomial PMF expression. Let's give ourselves a new page here. So again, it's the probability mass function for x, that x takes the value I. Let me say that in general, we use I here as the argument of these discrete random variable functions as a reminder that these random variables only take positive integers as values. Okay, there's no probability of 1/2 in the binomial story. Binomial random variables about either a success or a failure. If you're getting into sort of partial successes and things like that, you better have a continuous random variable. Okay, but right now we're just in the world of very clear, it's either this or it's that, it's heads or it's tails. It's this dichotomized thing. And again, the using the I as a symbol is kind of reminding us of that fact. But the probability that x takes value I is in choose I times the probability of a success in an individual trial raised to the I power times the probability of a fail in an individual trial raised to the power n minus I. Okay, so just without using numbers, wrapping our brain around what's going on in this formula, let's look at this part. This is the probability of I successes followed by n minus I fails. Okay, so thinking back of our n equals 3 case, this would be, and let's think about n equals 3 and the probability of 2 successes. Okay, so we're doing 3 coin flips. What's the probability that 2 of them are successful? Well, one way that can happen is to have success, success, fail. Okay, and so that's part of the overall probability. But this is not the only way, in most cases, that that can happen. So what we need to do then is multiply it by the number of different ways to choose, I'm putting choose in quotes here, the position of the I successes among the n trials. Okay, so what we're doing when we multiply by n choose I is we're saying, well, hey, yeah, that's fine. SSF is one way to get I equals 2, but so is SFS, so is FSS. Okay, and so multiplying by that 3 choose 2, which would equal 3, would account for the fact that we're just counting successes. We don't care if they all come at the beginning for the binomial or they all come at the end or whatever. Okay, so that's the logic behind behind this formula. The other random variables that are based on Bernoulli trials have kind of a similar logic behind them. I'm going to talk about them a little bit in the next lesson. So I'll see you then.